The public web is a goldmine of information, often structured using RDF and schema.org. However, this data is incredibly messy. Many types appear only a few times, predicates are inconsistently filled, and the sheer volume makes storage and querying prohibitively expensive. We need a way to reduce these massive knowledge graphs while keeping the information people actually use. The goal isn't just to make the graph smaller, but to make it smarter by shedding long-tail clutter. This process involves a two-step pipeline. First, we simplify the graph at the type level to identify core entities like products or books. Second, we perform a deep dive into predicates for those surviving types to ensure only the most informative properties remain. By the end of this pipeline, we transform a noisy data swamp into a streamlined, high-quality knowledge graph. To manage millions of entities, we start by abstracting the graph into a type interaction view. Instead of looking at individual triples, we build a compact graph where each node represents a schema.org class. Every original triple contributes to a count between subject and object types. For example, if a triple links a specific book to an author, we increment the count for the edge between the book type and the person type. We also include a literal sync for data that isn't a link to another entity. To make sense of these connections, we normalize the weights from two perspectives, the outgoing probability, P-out, and the incoming probability, P-in. This normalization allows us to see not just how often types connect, but how significant those connections are relative to the rest of the graph structure. Once we have our interaction graph, we need a way to score the importance of each type. We calculate a prominence score, S sub t, using 4 key factors. First, we look at the entity count, C sub t, which is how many entities actually use that type. Second, we use a depth weight, D sub t, where types closer to the root of the schema hierarchy are weighted more heavily. Finally, we run the PageRank algorithm in 2 passes, forward and reverse, to see how often a type is traversed in the network. These factors are combined into a single formula, where the entity count and depth are given lower exponential weights for stability, while the PageRank scores are combined with a 3-to-1 weighting. This balanced approach ensures we don't just keep the most common types, but also the most structurally significant ones. With our core types settled, we turn our attention to predicates, the properties like name or price. To decide which predicates to keep, we compute 5 statistical features for every type predicate pair. F sub p measures the fraction of entities using the predicate. U sub p tracks uniqueness, looking at distinct values versus total pairs. H sub p calculates the entropy of the values, helping us find fields with rich, varied information. Q sub p measures how often this predicate appears alongside others, indicating its role in a complete record. Finally, R sub p represents the share of random walk traversals that touch this specific predicate. By min-max scaling these features, we can create a combined structural and data score that highlights properties that are both consistently used and highly informative for that specific type. Sometimes statistical scores alone aren't enough, so the system uses a hybrid filtering mechanism. A small neural network featuring 2 hidden layers of 16 and 8 nodes is trained on manual review decisions. It takes our 5 statistical features as input and outputs the probability of keeping or discarding a predicate. The final decision follows a specific logic. If the statistical score and the neural model agree, we accept that decision. If the neural model wants to keep a predicate that the score system rejected, we prioritize the model to ensure high recall. If the model suggests discarding but the score is high, we use a rescue formula to see if the predicate's weight is significant enough to stay. This multi-layered approach ensures that even semantically important but statistically rare predicates have a chance to be preserved. The results of this pipeline are striking. In type pruning, the system successfully identifies core structural types like book, person, and product, while discarding low interaction tails like payment method or article. For specific types, the predicate filtering is equally effective. For a postal address, it keeps essential fields like street address and postal code while dropping rarely used ones like telephone or email in that context. For product entities, it correctly identifies name, SKU, and brand as core attributes. The entire system is implemented in Rust for high performance, providing a fast pipeline that shrinks the graph while maintaining its central descriptive power.
Future work will focus on even more advanced techniques, such as identifying strong predicate pairs and cautious entity merging to further refine the knowledge graph.